I see a dog, a car, two trash cans, a bicycle, and maybe a scooter. I would say I'm 85% confident that it's a scooter that pizza delivery guys use. Or perhaps I'm mistaken. Maybe it is a giant helmet on the scooter. Except for this last object, I'm confident about the rest of the objects in the picture. As such, I also see trees and pillars, but I'm going to ignore them as they are of no interest to me. The big question here is, how could I make my machines identify the objects as quickly and as precisely in any image like the way I did here? Let's explore what is all involved in order to make it happen. This image, or any image for that matter, would be fed into a system we call a detector. The predictions of that detector would be the bounding boxes around the objects, the classes or the categories to which they belong, and the probability or score associated with the respective bounding boxes. As you saw earlier, even as a human being, I was assigning an assurance level to various objects. Some I was 100% confident about, while some I was not. And therefore, it is critical that the computing systems we design and create do that as well. Clearly, making a system do what I did is no easy task. So this detector of ours is going to be a sophisticated system. And one way to tackle sophisticated or complex things is by starting to break them down into parts. Hopefully simpler parts or simpler components. For now, let's see the detector as a system consisting of three components. Since images come in various sizes, the first component's responsibility could be as simple as resizing them, so that the input to the next component is always of the same size. Actually, as part of pre-processing, we do a bit more than just resizing, but for now I would not go into more details about it. The second component is what I call the model. A model approximates the physical process or the physical reality. I am a human and I could see the objects in the image, and I intend to build a computer vision model that could do something similar. Since it is a model, an approximation, it would not be as good as you or me at this task of detecting objects. So most likely we will need a third component where the results of the model will be post-processed so as to refine the predictions it made. I'll talk about the post-processing a bit more later, so let's focus on the model now. In past, various statistical techniques and algorithms were designed to build object detection models, but yes, given the current state of art, this model is going to be a neural network. Therefore, to make it appear like a neural network, I first transform this square into a trapezoid. Something like this. The reason I represent this block or this model or this neural network using a trapezoid is because it shows that it is converting a high dimensional input into a low dimensional output. Look at the edge on the left, the one that I have highlighted using yellow. It's longer. The one on the right, that is the output of this network, is relatively smaller. Therefore, a trapezoid is generally used to represent a neural network that can transform a high dimensional input into a relatively low dimensional output. The next obvious question is which type of neural network it is. Since we are dealing with images, mostly it is going to be a convolutional neural network. For example, here is a list of various convolutional neural network architectures that have been invented to do image classification. By the way, there are more of them than what I'm showing you here, but this list does show some of the famous ones. And more importantly, you can find the implementations of these architectures as well as the pre-trained weights of these architectures at the URL mentioned on the screen. Now, the networks listed earlier were primarily designed to do image classification. However, for us, we are only interested in obtaining the last features of those networks, and therefore would ignore the layers that do the actual classification. I am showing this last layer, which is the shorter edge of our trapezoid, using a green color. The last feature layer is also called the representation layer, last representation layer, and also called the last feature map. we like to give many names to the same concepts in this domain. We then take these last features or representations and feed them into another neural network where the object detection task is performed. You can see that we removed the classification specific layers and added the detection specific layers. This network that contains additional layers for object detection task is called a head or a detection head. Since we are calling these additional layers the head, we can call our neural network that gave us the features a backbone. Backbone connected to head. Now the reality is that this backbone has multiple layers, and different levels or layers capture different types of information or represent different aspects of your input image. So an obvious thought is that just by relying on the last feature map or last representation, are we leaving something on the table? Could we perhaps make use of the features from various other layers at various depths in this backbone? Here is what we could do. See the green bars inside the backbone. They represent the features at various depths in the backbone. And we can introduce dedicated heads for each of these features. In this illustration, I have 3 feature maps, so I have 3 heads, one for each feature map. Perhaps we can take it even further. Instead of directly feeding the feature maps from different levels into their respective heads, we can refine them. The refinement step would involve yet another set of neural network layers, where some mixing, upsampling of these features could happen. And the output will be the so-called refined feature maps still being fed into their respective heads, as you can see in this diagram. Again, following the spirit of naming these neural networks, we could call these additional set of layers the neck of the final model. Backbone, neck, and the heads. Seems to make sense, huh? You probably know that, but just to be on the same page, we know that the deeper you are in the neural network, the representations or the features, they become more abstract. And the deeper you go, the receptive field increases also. You can say that the deeper level features and therefore the corresponding head will be responsible for detecting big objects, whereas the features near the input of the backbone would be good for detecting smaller objects. Of course, what I said earlier would only make sense if you know what is meant by the receptive field of a neural network. There are some good articles on it, by the way, and maybe I will explain in detail in some follow-up tutorials. But in brief, the answer is yes. The head for the deeper level features will detect big objects, and the one for the features near the input will be good at detecting small size objects. So how do we train this model? The first thing you want to do is to see all these networks, that is the backbone, the neck, and the heads, just as 3 components of a big full neural network. You can see that these components are connected to each other. So we would train this model end to end and may decide to use a pre-trained backbone for a faster convergence. But that pre-training part is really not required or essential anymore. Not in these days at least. Training will involve concepts that you are generally familiar with in the supervised training regime. That is, first and foremost, you need an access to the dataset with ground truth label information. Label here means the bounding boxes and the classes of the objects inside those bounding boxes. You would need the loss function, an optimizer, a metric to evaluate if your model is generalizing or not. Of course, various data augmentation tricks so that not only you can artificially increase the size of your data set, but you also show your training procedure possible distortions of your images. But I wish it was as easy as I have made it appear. Training here is not that straightforward. Unlike the ground truth labels and the loss functions that one is generally familiar in the image classification domain, there are some challenges here. Let me try to illustrate the challenge. Here is the traditional setup of image classification. You have a data set in which every sample has an associated label. Think of sample X as an image and Y as its class. For example, the yellow X has a yellow Y label. And in this data set, there are 3 classes only. You have a neural network whose last layers has 3 neurons. And you can see the symmetry here. Three classes or 3 categories, and therefore you have 3 neurons in the last layer. And if you send the yellow X to this network, it should give the highest value to the yellow neuron. Basically, there is one-to-one mapping. But in the object detection, we have a very difficult situation or a different situation. Look at our image again. Think of it as one sample, and to this sample are associated multiple objects. These objects are of different sizes and belong to different classes, and some may do belong to the same class as well. So you can see that the ground truth labels are variable here. They are not fixed, unlike your image classification problem. So the natural question is that would the prediction be variable too? And the answer to that is no. The model that we have, the neural network that we have, is going to predict fixed number of things, fixed number of bounding boxes, and associated with them their respective classes. So this is where most likely we use the post-processing stuff in order to refine or extract the predictions that are made by the model. And I hope you have started to understand that this entire setup can easily become computationally challenging and, more importantly, difficult to train. For example, one simple thought could be that in order to come up with a fixed number of predictions by our model or neural network, we assume that we are predicting a box at every pixel in the image. So here, let me lower your concern just a little bit, if not by a whole lot, by mentioning that we are using features to make the prediction. So we can say that we are predicting the box at a pixel or a cell in the feature space. This feature space is low dimensional regarding its width and height than the input image. Nonetheless, for a given input image, the model still would be predicting a very large number of boxes. Now, when we face situations like this that could require a lot of computations and perhaps not even have convergence during the training of a neural network, one remedy could be to inject some domain knowledge. In statistics, the domain knowledge is called the prior, something you already have some idea about or something you already know. I will have a dedicated and detailed tutorial on this, but long story short, we will essentially predict a set of bounding boxes at every pixel in the feature space. Note that I have said again feature space and not the input image space. There will be more than one bounding box at every pixel in the feature space, and these boxes will differ from each other based on their width and height. We'll come up with some width and height based on our domain knowledge, or which we call prior. But how do you figure out the width and height of these bounding boxes that you start with in the image or in the feature space is another tutorial that I'm going to do next. For now, just be content with this notion of prior boxes, which are nothing but our assumed boxes of certain scale and aspect ratio. Now, if you already have some background in object detection, you may know them as anchor boxes. Unfortunately, the challenge does not stop here. Let's say that we have these prior boxes or anchor boxes assumed at every pixel in the feature space, but how do we associate them with the ground truth boxes? This is considered a label assignment problem. There are plenty of algorithms and techniques to do that as well, and I will talk about some of them, the more recent ones, in the upcoming tutorials. Now that we are aware of the notion of the anchor box or a prior box and its association with the ground truth box, we can start to formulate our machine learning task as minimizing the distance between the types of boxes. For example, the blue box here represents a prior box, the one that you assumed, It's of certain scale and aspect ratio, the one that you came up with as your prior, and the green is the ground truth box. A box in this setup is specified or defined using the four corners, and the goal here is to learn the weights of the network in such a way that we reduce the distance between the corners of these boxes. You can think of this as a regression problem that uses 4 data points. Another way to think about it is that you are adding offsets to the coordinates of your prior boxes or anchor boxes such that the final result is that of a ground truth box. Now, this was just an example where I have used 4 corners to define the bounding boxes. As such, there are few different ways to specify the bounding box. For example, you could use the center of the box and its width and height as its specification. The loss will still be a regression loss, and it will be using those 4 things. Here, you are using 4 corners. If you are using center and the width and height, you still have 4 points. So the loss is still going to be the regression loss to figure out whether the offsets that we are predicting for the anchor boxes are bringing our anchor boxes closer to the ground truth boxes or not. Finally, as you know, we are not just learning the weights to predict the bounding boxes, or rather the offsets to the ground truth boxes, but we must also provide the associated classes. And hence, we need to include classification loss as well. Now, minimizing classification loss would come with another sort of challenge. As I said earlier, you would be assuming the anchor boxes on every pixel in the feature space. However, the number of boxes that would end up getting placed on the actual objects would be way smaller than the ones that you would end up placing on the background of the image, or the place where there are no objects of interest. Say you are interested only in detecting 3 objects. The prior boxes that do not get placed on those objects of interest now belong to the background class. So technically, you may think that you are doing classification for 3 classes, but reality is that you will be doing classification for 4 classes. It's a 4-class problem because the additional class will be that of a background. And this would result in class imbalance because you would have many more boxes placed on the background of the image. Let's talk about the post-processing component of our model now. The heads generate the predictions of the bounding boxes and the class labels along with the scores or their probability. During training, we would compute the loss and then compute the gradients. But during the actual test time, we don't have the access to the ground truth labels. The network is still going to make thousands of predictions. This is where the post-processing component will have a role to play. As you can appreciate, during test time, we would like to discard most of the predictions using the probability or score associated with them, and as well discard similar looking bounding boxes. Let's see using an example. Assume we have a successfully trained network, and during test time we pass this image to the trained network. For the dog in the picture, the network is going to predict many bounding boxes shown using the blue color. As you can see, these boxes are not that bad, but we must pick one of them, probably the best one, the best bounding box out of them. But which one is the best out of them, and how do you select it? This is where you will use one of the post-processing algorithm called non-maximum suppression. There are also some variants of this algorithm as well. Finally, how do you evaluate or judge the model's performance? Although evaluation metric in the field of object detection builds upon standard metrics like precision and recall, there is some confusion and variance here depending on the benchmark. The metric is universally called mean average precision, but there is a whole complexity and confusion with respect to the thresholds used and whatnot. In my opinion, having a good understanding of this MAP is essential to this field. Another component that gets used during both training and test as well as within the non-maximum suppression and MAP is a concept called intersection over union. Take these two examples. Take these boxes as example. Two boxes, the blue and the orange. Clearly, these boxes do not have any overlap. We say that the intersection over union of these two is 0. In this scenario, there is some overlap, and we must have some number that quantifies how much amount of overlap there is. Finally, this is a perfect overlap, and we say that the intersection over union is 1. This intersection over union, or IOU in short, is one way to measure the quality of your prediction. And as I mentioned earlier, it is also used from other components like NMS in the detection system to exclude the more similar bounding boxes. Nowadays, there are many variants of this IOU, for example, CIOU or GIOU, and we'll go over them as well in the subsequent tutorials. Finally, there is a lot of research and experimentation on what could be an ideal backbone for object detection, what are the different type of necks you can have, and of course the heads. I'll talk about some of the interesting arrangement of these layers in these backbones and necks that not only enhance the accuracy of your model, but also are capable of reducing the time it takes to make the prediction. Essentially, there are some recent advancements which can give you both accuracy, a good accuracy or a better accuracy, as well as at a faster inference time or prediction time. So far, I have only mentioned the main components and concepts that are required to make object detector. Reality is that there are many more nuisances and complexities associated within this field. For example, how do you even curate a data set for this computer vision task? And please also assume that we may be dealing with big data and or appreciate that some permutations and combination of things will make our life very difficult. So you should think about solving these issues systematically and productively instead of some ad hoc methods which work for short time but fail as your project or a system grows. What about various data augmentation strategies? Do they work? Are they difficult from the ones we do in image classification task? Yes, they are, by the way, and they do have an impact on training procedure. For example, there is a famous augmentation technique used in object detection called mosaic images that are created by combining various images. But how do you write the corresponding software components? How do you write a data loader or a transform which does it? Heck, how do you write more maintainable code in the first place? So far, what I have seen in this field of object detection with respect to code quality, it has not left a good impression on me. Sorry for a little critique here, but good quality code is of utmost importance to me. So, how do we learn more about these topics? Well, lately I have been working in this domain and have acquired some knowledge. So, let me give a shot at trying to explain the concepts I know. And I will explain the ones that I have mentioned so far, as well as the ones that I did not even bring up in this overview tutorial. And I assure you there are quite many of them. Hopefully they would be of some help to you, and I would also get to learn more about them as I make these tutorials, because once you explain a concept to somebody else, you actually end up learning a bit more about them. With that, I would like to say thank you for going through this tutorial. See you next time, hopefully sooner. Bye bye.